Professor, we can't hear you.
All right, let me continue. I might have been muted, but I hope that it was picked up on the Zoom. We'll see. In any case, all of the work is certainly in the video. Let me continue. So let me just review this particular problem. This is on page 288, number 55 on Fermat's principle. We have two poles, heights m and n, distance d apart. You take any point on the ground between them and draw taut wires, lines if you like, from that point to the tops of the two poles. And we want to choose x to minimize this distance. So this distance by the Pythagorean theorem is the square root of x squared plus m squared. And this distance by the Pythagorean theorem is the square root of d minus x squared plus n squared. So I expand that and I differentiate and I set the derivative equal to 0, and I get an equation that looks like this. And I just clear the denominator, square both sides, and I still have to solve this equation for x. This is x squared minus 2dx plus d squared plus n squared. And this is x squared minus 2dx plus x squared times x squared plus m squared. So that's an ugly looking equation, but let me see if I can solve it. Let me just multiply through. This is x to the fourth minus 2dx cubed plus d squared plus n squared times x squared. And when I multiply this, I get x to the fourth plus, oops, not plus, minus, oops, and this is a d, this is m squared. Sorry, this is x squared minus 2dx plus d squared. So I get this fourth degree term. I get one cubic term minus 2dx cubed. I get some quadratic terms. I get d squared x squared and m squared x squared. So I have d squared plus m squared x squared. And I have a constant term, d squared m squared. So I have 1, 2, 3, 4. I should have 6 terms. Let's see. X to the fourth, m squared x squared, minus 2dx cubed, the linear term, minus 2dm squared x, d squared x squared, and d squared m squared. And I have some cancellation. X to the fourth, they cancel. Minus 2dx cubed canceled. So I have this equals this. So I really have a quadratic equation. I have, if I bring this onto the other side, I subtract, I get m squared minus n squared x squared minus 2dm squared x plus d squared m squared equals 0. So if I've done my algebra correctly, I just have to solve this quadratic equation. You know, since I'm always suspicious of my work, I'm just going to go back and double check this for 1 second. This is the distance. The sum of the distances. This is the total length of the wire. If I differentiate this, I get x over the square root of x squared plus m squared plus d minus x or x minus d. X minus d. So this has to equal this. I cross multiply. I expand this. Let's see, x to the fourth minus 2dx cubed. X to the fourth minus 2dx cubed plus d squared plus n squared times x squared equals x to the fourth minus 2dx cubed d squared plus m squared x squared. And hopefully this is good. So I have to solve this equation. So by the quadratic formula, x is equal to minus b plus or minus the square root of b squared minus 4ac over 2a over 2 m squared minus n squared. Well, that's the answer. So again, I can actually simplify this a little bit because I can factor out a 2d m squared. Now, let me expand this a little bit more. This is 2d m squared over 2 m squared minus n squared plus or minus the square root. And what I have in here is 4d squared m to the fourth minus 4, oh, this is nice, d squared m to the fourth plus 4n squared d squared. So these cancel, and this is square root of 4n squared d squared is 2nd. So this looks like 2d m squared plus or minus 2 dn over 2 m squared minus n squared. The 2's cancel. And it would be nice if this were an n to the fourth instead of an n squared. Let's just see where that came from. B squared minus 4 AC. Let me draw my picture. So this is M, this is N, this is X. And the point X, which is the critical point of this function, is we're solving a quadratic. So we have dm squared plus or minus dn over m squared minus n squared. But something is wrong because this shouldn't be a square if this is a square. They should have the same degree. So I just want to go back and double check my work again. It's easy in doing the algebra for calculus to make a mistake. So this is square root of x squared plus m squared and square root of d minus x squared plus n squared, which is x squared plus m squared to the 1/2, x squared minus 2dx plus d squared plus m squared to the 1/2. When you differentiate that, you get x over the square root. And here you get, when you differentiate, 2x minus 2d, or 2 times x minus d, over that square root equals 0. So this equals this, and bring this over to the other side. So x times the square root of d minus x squared plus n squared equals d minus x times the square root of x squared plus m squared. Square both sides, I get this equals this, x squared minus 2dx plus d squared plus n squared, x squared minus 2dx plus d squared, x squared plus m squared. Multiply through x to the fourth minus 2dx cubed plus d squared plus n squared times x squared, x to the fourth minus 2dx cubed plus m squared d squared, x to the fourth minus 2dx cubed plus d squared x squared plus m squared x squared minus 2d m squared x plus d squared x squared. That seems okay. These cancel. So I have, and d squared x squared cancels d squared x squared. So I have m squared minus n squared x squared minus 2d m squared x plus d squared m squared. So I'm left with 4 terms. M squared x squared minus n squared x squared minus 2d m squared x plus d squared m squared equals 0. So by the quadratic formula, x is equal to 2dm squared plus or minus the square root of this squared minus 4 times m squared minus n squared times d squared m squared, b squared minus 4ac. So that's 4 d squared m to the fourth minus 4 d squared m to the fourth plus 4 n squared d squared m squared. See, that term had disappeared. So that's equal to 2dm squared plus or minus the square root of 2d mn. Aha, that looks a little bit better. So x is equal to dm squared plus or minus d mn. If I can factor out dm, this is dm times m plus or minus n over, and this factors into m plus n, m minus n. And x is no bigger than d, so if this were dm over m minus n, that would be bigger than d. If it's dm over m plus n, so let's make this m minus n, these cancel. So we get dm over m plus n. Aha. So we solved our problem. This is 0, this is d, this is m, this is n. This point that minimizes the length of the wires is dm over m plus n. So that's what this distance is. And this distance from here to here is d minus dm over m plus n. which is d times 1 minus m over m plus n, which is dn over m plus n. So this angle, theta 1, what is theta 1? Tangent of theta 1, opposite over adjacent, is m over dm times over m plus n. The m's cancel. This is m plus n over d. This angle is theta 2. The tangent of theta 2 is equal to n over dn over m plus n, which is the same thing, m plus n over d. So theta 1 and theta 2 are angles between 0 and pi over 2. They have the same tangents, they're equal. So you get the shortest length of wire when theta 1 equals theta 2. That's Fermat's principle, one form of Fermat's principle. That's very good. Sorry about the sound. The first part was really just reviewing the applications of the derivative. So I can certainly answer questions about that if you have questions on Wednesday. All right. So up to this point, we were dealing with the following problem. Given a function, f of x, find f prime of x. So f of x equals x cubed minus 2 sine x, then f prime of x is 3x squared minus 2 cosine x. That's the derivative problem. But I want to reverse it. I want to do the following problem. Suppose we're given the derivative f prime of x, find f of x. So that's the opposite problem. It's going in the opposite direction. We can call that the antiderivative problem. So if f prime of x is 3x squared minus 2 cosine x, then f of x, well, at least one solution is x cubed minus 2 sine x. Well, let's make it easier. Suppose f prime of x is 2x. What's an antiderivative? F of x equals x squared. Now, there's an ambiguity here, which is very important to emphasize. If I give you a function, there's only one derivative. But if I give you a derivative and I want you to find the function, well, there's more than one answer. If the derivative is 2x, the function could be x squared. Or it could be x squared plus 1, because the derivative of 1 is 0. Or it could be x squared plus any constant c, because the derivative of c is 0. So we have this ambiguity in the antiderivative problem. You can always add a constant to any solution of the antiderivative problem because the derivative of the constant is 0. So let me restate this a little bit. So this is more of the notation which the text is using, but it's equivalent. It's the following. This is the definition. A function capital F is an, I can't say the, is an antiderivative of a function f on an interval I, if the derivative of capital F is equal to little f for all x in the interval I. So for example, if f of x is, I don't know, e to the 2x, an antiderivative, capital F of x, would be a half e to the 2x, because if you differentiate this by the chain rule, you get e to the x. If f of x is 7x cubed plus 2x squared minus 19, what's a function whose derivative is 7x cubed plus 2x squared minus 19? Let's see, what's an antiderivative of x cubed? 1/4 x to the 4th. So capital F of x could be 7 over 4x to the 4th. That would give the first term, because if I differentiate this, the 4's cancel, I get 7x cubed. An antiderivative of x squared would be 1/3 x cubed. And an antiderivative of 19 would be 19x. In fact, we have the following. If f of x is x to the n, what's a function whose derivative is x to the n? Well, if I differentiate x to the n plus 1, I get n plus 1 x to the n. I don't want the n plus 1, so 1 over n plus 1. So if I differentiate this, the n plus 1's cancel, and I just get x to the n. Of course, there's one time this doesn't work, because you can't divide by 0. This is for n not equal to minus 1. If n were minus 1, this would be 0. What about n equal to minus 1? If f of x is x to the minus 1 or 1 over x, well, we saw that the antiderivative of 1 over x is the log of x, because the derivative of log x is 1 over x. And in all these cases, you can always add any constant, because the derivative of a constant is 0, so adding a constant doesn't change anything. Any questions about this so far? And now we come to one of the basic notational parts of calculus. How do we notate? How do we denote the antiderivative? We use what is called an integral sign. So this is notation. The antiderivative of f of x is written as this symbol. It's called an integral sign, f of x dx. So, for example, for n not equal to -1, the integral of x to the n dx is 1 over n plus 1, x to the n plus 1, plus any constant. This is actually the most important antiderivative. Well, or one of the 2 or 3 most important antiderivatives. So a large part of second semester calculus is learning how to compute antiderivatives for complicated functions. There's some simple examples, but there aren't a lot of simple examples. Some we can just do by trial and error. Suppose we want to find the integral or the antiderivative of the function 3x to the 5th minus 5x to the 9th. So an antiderivative of x to the 5th would be 1/6 x to the 6th. If you differentiate this, the 6's cancel, you get x to the 5th. And if you multiply that by 3, when you differentiate this, you'll get 3x to the 5th. An antiderivative of x to the 9th would be 1/10 x to the 10th. Because if you differentiate this, the 10's cancel and you get x to the 9th. So if I multiply this by 5, the derivative would be 5x to the 9th. So this should be the answer, plus a constant. What is this? This is 1/2 x to the 6th minus 1/2 x to the 10th. And you can check, if you differentiate this, you get 3x to the 5th minus 5x to the 9th. So that works. Just using this fact. Or to make it a little bit more complicated looking, suppose you want to integrate or find the antiderivative of 4 times the square root of x minus 4 over square root of x. So let me write everything as powers of x. This is the integral of 4 square root of x is x to the 1/2 minus 4, 1 over the square root of x is x to the minus 1/2 dx. Now this power rule works for any numbers, not necessarily whole numbers. It works for fractions, for example. You increase the exponent by 1, n to n plus 1, divided by n plus 1. So an antiderivative of x to the 1/2 would be 1 over 1/2 plus 1, x to the 1/2 plus 1, minus 4, x to the minus 1/2 plus 1, 1 over minus 1/2 plus 1. So if you do your arithmetic correctly, this is 1 over 3/2, which is 2/3. X to 1/2 plus 1 is 3/2. This is 1 minus 1/2, which is 1/2. So 1 over 1/2 is 2 minus 4 times 2, x to the 1/2. So this is equal to, write it over here, 8/3 x to the 3/2 minus 8 x to the 1/2 plus a constant. And you can check, if you differentiate this, you get 4 times the square root of x minus 4 over the square root of x. So that's exactly the right answer. All right. Any questions about any of this? Let me just state some properties of antiderivatives, or if you like, of integrals, that come from basic properties of derivatives. So we know that if you take the sum of two functions, f plus g, and you differentiate it, that's the sum of the sum of the derivatives. And if you take a function and multiply it by a constant, you get constant times the derivative of the function. So if we have antiderivatives, capital F and capital G, then f prime equals f and g prime equals g. So f plus g prime equals f prime plus g prime, which is f plus g, which means the antiderivative of f plus g is f plus g, which is the integral of f plus the integral of g. So we have this very nice additive property for integrals. The integral of the sum of two functions is the sum of the integrals. And similarly, the integral of a constant times a function, you can take the constant outside the integral sign as constant times the integral of the function. So we have these two fundamental properties of antiderivatives, the constant multiple rule and the sum rule. And we can do a lot using these simple rules and the facts that we know. Because whenever we have a derivative formula, we have an antiderivative formula. The derivative of the sine of x is the cosine of x. So the antiderivative of the cosine of x is the sine of x plus a constant. The derivative of the cosine of x is minus the sine of x. So the integral of minus the sine of x is cosine of x. Or if I take out the minus sign or multiply by -1, the integral of the sine of x is minus the cosine of x plus a constant. So you need to spend a lot of time practicing the calculation of antiderivatives. The integral of secant squared of x dx. What is a function whose derivative is secant squared? Well, you have to remember these things. It's the tangent. So it's tangent of x plus a constant. And so on. The integral of 1 over x dx is log x plus a constant. The integral of e to the x dx, the derivative of e to the x is e to the x, so the integral of e to the x is also e to the x, plus, of course, any constant. Now, there is some algebraic skill you need when you're trying to solve more complicated looking integrals. Suppose we have 4x cubed plus 2x over 3x squared. We want to integrate that. So what we can do is try to rearrange this integrand, the function we're trying to integrate or find the antiderivative of. Let's see, how can we do that? 4x cubed plus 2x over 3x squared, just by fractions, 4x cubed over 3x squared plus 2x over 3x squared. That's 4/3 x plus 2/3, 1 over x. Aha. So this is the integral of 4/3 x plus 2/3 times 1 over x. So using the fact that the integral of the sum of two functions is the sum of the integrals, this is the integral of 4/3 x dx plus the integral of 2/3 1 over x dx. And using the fact that you can take a constant outside the integral signs, this is 4/3 the integral of x dx plus 2/3 the integral of 1 over x dx. The integral of x to the first power is 1/2 x to the second power. The integral of 1 over x is log x plus a constant, or if you like, 2/3 x squared plus 2/3 log x plus a constant. Let's look at another one. Again, these are all techniques you have to maybe invent if you haven't seen them before, but spend a lot of time doing this kind of algebra and calculus, and you'll do very well on the final. Suppose we have the integral of 5x squared over 4 plus 4x squared. So dx. So this is complicated. I can't solve that just by looking at it, but I can see if I can do something to make this, put this in a form that is easier to work with. So let's see, 5x squared over 4 plus 4x squared is 5x squared over 4 times 1 plus x squared. So that's 5/4 x squared over 1 plus x squared. That doesn't help me too much. So I'm desperate. I'll try something. I'll invent something. X squared over 1 plus x squared. If I made this 1 plus x squared minus 1, I've just added 0, 1 minus 1, so that's okay. So this is 5/4 times 1 plus x squared over 1 plus x squared minus 1 over 1 plus x squared. And this is just 1. This is 5/4 times 1 minus 1 plus x squared. So I can write this function as this. I can take the 5/4 outside the integral sign. This is 5/4 the integral of 1 minus 1 over 1 plus x squared dx. So that's 5/4 times the integral of 1 dx minus the integral of 1 over 1 plus x squared dx. What is that? Well, 5/4. The integral of 1 is x. And if I can remember that the derivative of the inverse tangent of x is 1 over 1 plus x squared. The antiderivative of 1 over 1 plus x squared is the inverse tangent of x plus a constant. Do one more. Suppose I want to find the antiderivative of 3u to the minus 2 minus 4u squared plus 1 du. Using the constant multiplier rule and the addition rule, this is 3 times the integral of u to the minus 2 du minus 4 times the integral of u squared du plus the integral of 1 du. And these are all powers of u, so I know how to differentiate that, to integrate that. The antiderivative of integral of u to the minus 2, if I add 1 to minus 2, I get minus 1. So I get 1 over minus 1, u to the minus 1. The antiderivative of u squared is 1/3 u cubed. And the antiderivative of 1 is u plus a constant. So this is minus 3 over u minus 4/3 u cubed plus u plus a constant. And you can check, if you differentiate this, you get 3u to the minus 2 minus 4u squared plus 1. Okay. All right, so this is our introduction to this very important topic of antiderivatives. Antiderivative or integrals. And we're really going to spend the rest of the semester studying these things. We have 8 more lectures and 1 more class. So if you missed this statement at the beginning, midterm number 2 will be Monday, May 1st, 11 o'clock to 12 o'clock in Gillette Hall on campus. So after the first exam, many people asked for a second exam, and I said, okay. So this is where and when it will be. Okay. Any questions before we quit for the morning? If not, sorry about the sound for the first part of the talk. And we'll be back on Wednesday. Okay, be well all.